When we started talking about diastereomers, we mentioned that if we have n stereocenters in a given molecule, we can have up to 2 to the nth different diastereomers. However, in some compounds, we don't get this maximal number of diastereomers, we get less. And this phenomenon is a consequence of the occurrence of the so-called mesocompounds, which are simply defined as achiral compounds with chiral centers. In these compounds, chiral centers are oriented in a way that makes them, in a way, cancel each other out. So sort of mirror images already to begin with. To illustrate this in an example, in a relatively symmetric molecule, such as this dialcohol, we can have 2 stereocenters. There's one here and another one here. If you look at the mirror image of this molecule, we'll notice that both of these compounds have a plane of symmetry. It's a common plane of symmetry here. And that furthermore, they're related by rotation. If you rotate this structure by 180 degrees, which we said is legal in the Fischer projections, we'll end up with the same structure. And so these 2 compounds are the same compound. Therefore, they count as only one diastereomer. Now, for the same molecular structure, we can come up with 2 other diastereomers, which really are different compounds. We can have this isomer, or we can have its mirror image. And these 2 really are enantiomeric because rotation by 180 degrees does not lead to superimposable structure. Okay? Now, in the case of this specific 2,3-dihydroxybutane, we have only 3 diastereomers and not the maximum of 4. Okay? And such compounds, mesocompounds in that case contribute to that phenomenon. If we look at the configurations of each individual schedule, here this will be R and this will be S, and I urge you to convince yourself of that. And here this will be S and this will be R. But since these compounds are identical, these configurations are just one read from the back versus the other one. In this case, we will have now R and R configuration and S configuration, which means that this 2,3-dihydroxybutane has SS isomer, RR isomer, and these are enantiomers of each other. And then there is the RS isomer, which is achiral mesocompound. As achiral, this compound does not turn the plane of polarized light at all. This is actually a common phenomenon, and you can see it in a number of different systems. If we have this dibromocyclopentane, even though we have 2 chiral centers here, this is still a mesocompound because you see a symmetry plane here. Symmetry plane in some cases can go through a chiral center. That's fine. If we have a case like this one, then our symmetry plane goes here, but it still makes the molecule achiral. If we switch substituents, the same thing happens as well. And all of these are mesocompounds. So to reiterate this once again, mesocompounds are examples of compounds which have typically multiple chiral centers, but in such an arrangement that the molecule overall has a plane of symmetry and is thus achiral.